Here's for the next topic, and that is net ionic equations in Unit 5, Aqueous Chemistry. Again, we do need to be reminded of these precipitation reactions in that and which ones are going to be soluble, which ones are not going to be soluble, because that's going to be important when we talk about net ionic equations. So the rules, how we have them written, again, are going to be very important when we start breaking up some of these things. It's going to piggyback off some of the things that I kind of did in some of the examples in the previous video. And so how I wrote some of them out is just going to be expanded just a little bit more. But it's going to, in a way, well, be a little bit more thorough, and we'll look at that in just a little bit. So, in the ionic equation, all of our electrolytes, strong acids, strong bases, and anything ionic compounds that are going to dissociate into their ions will make these things up. What's this going to do is it kind of gives us a more actual accurate depiction of what's actually things look like in the beaker or the Erlenmeyer flask or wherever, of what it actually looks like, in that these ions are kind of just floating around as we see them. And as we can see here, the net ionic equation is what we're going to try to do is we're going to try to break everything up as on the reactant side. That's the top line here is the reactant side. And you can see above that line that's the reactants, and below is the products. And now we should know that the silver and the nitrate that came from somewhere. Where did that come from? Well, that came from the silver nitrate. And the potassium and the chlorine came from potassium chloride. When you write these all out, and you kind of saw this when I was doing some of the examples, is I would write them into their ions. So, and it serves a couple purposes. And that one, we can, when we're doing regular double replacement reactions, we can actually see the charges, and so that we get our charges done correctly. And net ionic equations are a way to kind of get rid of the fluff, the stuff that really actually doesn't matter in the chemical reaction as we are actually utilizing it. And so it does have its place, and we will use them here and there. But they kind of break everything down, and then we can see below the line that the silver chloride is together because it's a solid. Anything that is a solid, liquid, or a gas does not get broken up into their ion forms, and so that's why we say the silver chloride doesn't. So they don't. So they don't break into their ions as we would see that. So solids, liquids, and gases. And there's, again, very few liquids in our line of work. Gases, we'll look at a couple of examples of those later on. As we continue through the stuff, I believe there's some on your master in chemistry. But solids are your precipitate. And again, so anything that would precipitate out is going to be that solid, and that's why we would write it that way. So the net ionic equation is how we get rid of it. Is we get rid of anything that is the same on both sides. And so we need to look at how things are written. Now, sometimes you're going to see these written out in a way that you're going to not have it top and bottom. It's going to be left and right, reactants and products. And so this is going to serve its purpose a little bit. So what we're trying to do is we're getting rid of all the fluff. Anything that actually doesn't matter to the reaction happening or not happening. If everything's crossed out, the reaction doesn't happen. But if you have something, if you have at least 1 to 2 things on the reactant side and 1 thing on the product side, or 2 things on the product side, then the reaction does happen. And so we're trying to get rid of that. A lot of times I utilize the analogy that it's like a wedding. For the wedding to happen, you just really truly need the groom, the bride, the priest and witnesses are pretty much everything. And what we look at as the people in the audience and why people go to weddings, they're just spectators. They're just there to watch the process happen. And that's what these ions that are looking at here is, they're just spectator ions. They're not actually taking part in it. They're not actually doing anything in the reaction. They're just going to watch it happen. And so that's why we look at them as just called spectator ions. And so we can see that nitrate is the same thing on both sides, and so we cross it out. And then we look and we can see that potassium is also the same on both sides, and so we cross it out. Now, silver and chlorine, they're not in their ion form on the product side, and because we can see here that on the product side, it's together, it's a solid. And so really what it comes down to is that silver and chlorine are, like the bride and the groom, and they come to form this marriage and making silver chloride. The other ions, the nitrate, the potassium, they're just considered to be spectators. They're not actually doing anything. And so we are able to remove them from the reaction, and so we can then utilize this to kind of like, what is this reaction actually looking for, or what am I looking for in this reaction based on the net ionic equation. And ultimately, this is what we're left with, is that silver 1, an aqueous solution of silver 1 and an aqueous solution of chlorine make silver chloride. What the silver is, if it's associated with an acetate or a nitrate, doesn't matter, because it's just going to be a spectator ion. It doesn't matter what metal the chlorine is attached with, because it's going to be just a spectator anyway. And so what we see here is that this is ultimately the bare bones, everything that's important from that reaction to kind of show us there. And it is going to have its process, and it's going to have its net, it's going to be, we're going to see everything with it. And so we'll look at some things further on. So some steps that we need to do is writing out a balanced molecular equation. So balancing things out, when you balance things out, it's up for some debate. I think sometimes people find balancing them later better than it is earlier. Sometimes people balance them out at the beginning and then do this, but ultimately we'll find sometimes it works one way, sometimes it's better to work the other way. So we'll just kind of work as we need. So dissociate all the strong electrolytes. So anything that is soluble gets split up, and we cross out anything that remains from either side. And so kind of get rid of the spectators, kind of the way a lot of sports are doing in 2020. Get rid of the spectators, and then just have the game be played, so to speak. But ultimately that's what we're looking at, is just there. Write the net ionic equation with the species that remains, meaning everything that's left. And because we don't want to say ionic compounds, molecular compounds, we just say the species that remains, just kind of whatever's left. Is what we see from there. Following these here again should give you a pretty step-by-step approach, but let's go over a couple of examples. So we're asked to write the net ionic equation for the following: a calcium chloride and a sodium carbonate, they're mixed. And so what does that mean for us? Well, for here, what we're going to want to do is we're going to take our calcium chloride and sodium carbonate. And so we're going to write calcium chloride is going to be soluble, sodium carbonate is also going to be soluble. So I'll need to split them up right off the bat, and it'll make life a little bit easier for us if we do that. And so we'll have calcium. If I look on my periodic table, it's where I get that. We know it's aqueous solution plus the chloride ion, which will also be an aqueous solution, plus, I usually try to have a little bit bigger of a plus between the compounds, so then we can kind of see where that comes from. And then our sodium ion is also going to be aqueous, and a little plus becoming then sodium carbonate, and it'll be our carbonate ion minus, and is also going to be aqueous. Now, when we come down to the what is this going to look like, we're going to utilize top and bottom again here. And so normally it would be again written out there, so would have that. But what we have now is calcium was dancing with chlorine, but is now going to dance with carbonate. Now we have to be careful again, paying attention to, is calcium carbonate is not a transition metal? Is it a soluble salt? And the answer is no, which means it forms a precipitate. And since we can see that, and we have these ions there, we can see that calcium and carbonate both have 2's, they would cancel out. And so we would have calcium carbonate, and it would be a solid, okay, plus sodium is now is aqueous. It is now going to dance with the chlorine, as we swing our partners do-si-do. And we can now finish off the whole process and say I see my chlorine is the same on both sides. My sodium is the same on both sides, or top and bottom of this reaction. And that ultimately, the final product of this reaction, after I got rid of my spectator ions, which so happen to be the sodium and the chlorine, that I have just a calcium ion when mixed with a carbonate ion forms the solid of calcium carbonate, which we also then would look at as limestone. Why do we have hard water? Well, that's because calcium carbonate lines a lot of our aquifers. And so that's the process that it has. And how does it form? Well, it's forming of these ions, not maybe that calcium chloride and sodium carbonate, but it's from these here. And so we can see that my final product is calcium, aqueous solution of calcium and an aqueous solution of carbonate. Make that. It does not matter what metal, well, it kind of does matter what metal the carbonate is. It's got to be a group 1, otherwise it wouldn't be soluble. But the calcium, for the most part, you'd have that as well. So if you have 2 insoluble salts as the reactants, you're going to not get a reaction because they're not going to break apart. So there's that too. So let's try another one. Barium bromide is mixed with potassium sulfate. Okay, So barium bromide, and some of you are like, well, I wouldn't want to eat that. Well, you're right. No one would want to eat barium bromide. And one of the rules of 3 is Rule 3 has 3 exceptions: silver, mercury, and lead. And barium is one of those things that you wouldn't want to ingest, but that kind of defeats that purpose. But we'll break it up anyway. And so, of your barium ion, that's aqueous, and we got maybe a little bit smaller of a plus sign there. And so we have plus bromide, Br with the negative, and it's aqueous, and is going to mix with potassium sulfate. And so we're going to have the potassium ion, and that's aqueous. Again, if you're wondering where those charges come from, you should look on your periodic table. And then we have our sulfate ion, and that is also aqueous. And what is that going to form? And now again, we're going to utilize, kind of top and bottom on this, and we're going to swing our partners do-si-do. So barium was dancing with bromine, but is now going to dance with sulfate. And so barium and sulfate make a insoluble salt, and they both have 2s on there. And so we can see that how that works is that they will have that barium sulfate solid, and then potassium, what that was dancing with sulfate earlier, is now going to be dancing with bromine. That's aqueous. And so now we can see that potassium is the same on both sides, bromine is the same on both sides, and that ultimately, again, my net ionic equation is aqueous aqueous barium when mixed with aqueous sulfate, a solid or precipitate forms of barium sulfate. And everything else are spectator ions. And so we'll look at this. And from here, we're going to start utilizing some, getting into looking at some acids and bases and some molarity calculations as well. So we're also have some other types of equations, single replacement reactions as well, that we still have to go through as we move through this unit.